Hi there, this is Astrophysics, Surveying the Stars, lesson 8, and this is evolution of the Sun, or any star that's around a similar size. So there's no calculations in this one. This is just a big explanation, how it all happens for those big 6-mark exam questions. So first of all, nebula and protostar. So a star is formed as dust and gas clouds, nebula, mainly hydrogen gas in space, and what that does, that collapses under its own gravitational attraction, becomes denser and denser to form a protostar, which is like a baby star type thing, typically around 1.5 million degrees Celsius. In this collapse, gravitational potential energy is converted into thermal energy as the atoms and molecules gain kinetic energy. And the interior of the protostar becomes hotter and hotter. If this protostar has sufficient mass, it's about 8% the mass of the Sun, or greater than 8% mass of the Sun in its current form, the temperature will increase high enough for the nuclear fusion of hydrogen to helium to occur in its core. And at that point, a star is formed, and then it'll just keep, bringing in mass and increasing in size. So we've got a nebula, which is basically a cloud of mainly hydrogen, but of elements as well, into a protostar. Protostar then, under its own mass and its own gravity, will start to collapse, and as it starts to contract more, it gets hotter and hotter, resulting in severe warming. And then it ends up on the main sequence, which is where the Sun is now. The warming will gradually continue, as we'll discuss now. So the main sequence. So a newly formed star reaches internal equilibrium as the inward gravitational attraction is balanced by the outward radiation pressure due to the process of nuclear fusion. And remember, a star the size of the Sun will be converting millions of tons of hydrogen into helium per second. So it's a crazy amount of energy. And the star will become stable. The main sequence is also known as the main stable period, and it'll have a near constant luminosity. It does vary slightly, but it's basically, for all intents and purposes, it's constant. So the greater the mass of the star, the higher will be its absolute magnitude and surface temperature, but the shorter the time the star remains in the main sequence. So smaller stars live longer, so the Sun, it's got approximately 10 billion year lifespan in total. Really, really big, these giant O-class stars, the big blue ones, that are at 40,000 Kelvin, they might only stay in main sequence for about 10 million years. So as I've said, the Sun's about halfway through its 10 billion year passage. And as I've said, largest stars only last for tens of millions of years. Well, on the main sequence, the star's absolute magnitude and surface temperature will gradually increase. So in about 2 billion years' time, the Earth will become too hot to sustain any life. So red giant. So once most of the hydrogen in the core of the star has been converted to helium, the core will begin to collapse on itself, and the outer layers of the star will expand. Because obviously, if you get all that energy and compress it into a smaller volume, the temperature will shoot up, and then it will cause expansion as the expansion of the star will be able to overcome gravity. So the star swells out, moves off the main sequence, and becomes a red giant. So if you remember the Hertzsprung-Russell diagram from last lesson, we talked about just to the right diagonal of the Sun. That's where the giants are. So the temperature of the helium core increases as it collapses, and it causes surrounding hydrogen to undergo fusion, which will heat the core even further. When the core reaches about 10 to the power of 8 Kelvin, compared to the Sun at the moment, it's around 15 million Kelvin, so it's quite a severe increase in temperature. Helium nuclei will begin to undergo fusion. So this forms even heavier nuclei, principally beryllium, carbon, oxygen. And the luminosity of the star increases as the star expands. The Sun is expected to achieve a radius roughly equal to the Earth's orbit. So when the Sun actually undergoes this red giant phase, it'll basically engulf the Earth. So Mercury, Venus, and the Earth, not Mars, no longer exist, and Mars will become the first planet in the solar system. So red giant phase lasts about 1/5 of the main sequence days. So in terms of our own sun, approximately 2 billion years. So planetary nebula and white dwarf. So when nuclear fusion in the core of a giant star ceases, the star will cool, and its core contracts, and the outer layers, because obviously this thing's so big now that the gravity is not, not very strong on it at the outer layers. So the outer layers will be thrown off of the star. So the outer layers are thrown off as shells of hot gas and dust to form what we call a planetary nebula. And the remaining core of the star is white hot due to the release of gravitational energy. And if it's less than approximately 1.4 solar masses, which our sun obviously will be, the contraction of the core stops as the electrons in the core can no longer be forced any closer. The star is now stable again and has become a white dwarf. So eventually it'll cool to invisibility, which is postulated to become something called a black dwarf. This process takes this process takes longer than the entire age of the universe, so no black dwarfs actually exist. White dwarfs do exist though. It could take 100 billion years. So quick recap: nebula, protostar. So gets hotter and hotter. Nuclear fusion starts to increase, mass increases, main sequence. Gradual warming on the main sequence. Star starts to become a red giant. Planetary nebula, and then white dwarf. Now you could be asked in exam questions about the changes in absolute magnitude and temperature as these processes occur. So it's really, really important that you know what's on the axis for absolute magnitude and the temperature axis on the x-axis. Anyway, we found that useful, and thanks for watching.